So, welcome everyone. So, we are discussing the hydrogen spectrum. So, in this class, in first part, we will first again recall what we have studied in the last class, the hydrogen spectrum, in a summarized way. After that, we will go into the last part of this of this chapter. We can say the ionization energy and the ionization potential part, and then we discuss the drawbacks of Bohr postulates. We are in now in the last position of the this Bohr's atomic model. First we have discussed, as we did know that first we discussed the Rutherford atomic model. After that we discussed the Bohr atomic we are discussing, and the hydrogen spectrum actually was justified, or we can say described, by the Bohr's atomic model. So that is the great success of Bohr's atomic model. So you are in that part in last class. So Bohr's atomic model was accepted, or well accepted we can say, rather, due to it was able to give the justification to the hydrogen spectrum. That was very you can say crucial for the for understand the atomic structure. So that's why the Bohr's hypothesis, or we can say Bohr's atomic model, is well renowned model. But there are some also drawback in this model. We will discuss that in the last part. And after Bohr's atomic model, Sommerfeld came, and Sommerfeld gave the Sommerfeld model, but that things are not included in this part, in this chapter. So we will not discuss those part. After completing the Bohr's atomic model, we will go into the X-ray part. We will discuss the X-ray part, and then this chapter will be completed. So let me start with the with revising the last part. So we are discussing hydrogen spectrum. Okay, hydrogen spectrum is a special kind of atomic spectrum. So we know this. What is the atomic spectrum? This part we have already discussed, but still, to make continuation, we are again discussing this part little bit. So atomic spectrum means, let's say if there is a discharge tube, and in very low pressure, if you fill that discharge tube with any gas, that may be hydrogen, that may be neon, that may be argon, any gas, and then if after putting that gas in that discharge tube, if you make electric discharge, that means if you pass electric current through the discharge tube, then lights, we can say heavy amount of lights is bright, that discharge tube actually act as a bright source of light, we can say. That is the quote unquote statement. And that light is analyzed as the atomic spectrum of that particular element. Let's say if you fill the discharge tube with hydrogen gas, then if you make the electric discharge on that discharge tube under very low pressure, few mm of Hg pressure, then one spectrum is coming out from the discharge tube, bright light, and you analyze that spectrum, then that will be called the hydrogen atomic spectrum, or atomic spectrum for the hydrogen atom. That's same thing. So there are very other discharge tube or discharge lamp we are actually used, just like sodium vapor lamp, neon lamp. These lamp are very common in use. So but the hydrogen atom spectrum was very important, because this was quite unexpected. The result, the spectrum obtained when the hydrogen atom was kept in the discharge tube, not only hydrogen atom, but also for other elements as well, but the hydrogen atom is the most simplest one. That's why we are dealing with the hydrogen atom case. But that hydrogen atom spectrum was not explained by the atomic theory given by the Rutherford gave the atomic theory, you know that, but there are some drawbacks, flaws. But the main problem was that this hydrogen atom spectrum was known before 90s. That means in the last of the 19th century it was very well known, but that was very we can say very suspicious thing, because there are some discreteness in that spectrum that was not explained by the scientists, because the known mechanics, known science was totally amazed with these results. So that's why Bohr atomic model is very important, because the Bohr, we know that we have studied Bohr atomic model. There are some ad hoc postulates. Bohr just considered those postulates. There are no physical justification behind those postulates, but still the results coming out from this Bohr hypothesis, Bohr's model, was able to justify this atomic spectra, hydrogen atom spectra. That's why the Bohr atomic model was accepted, well accepted rather. So that is the main thing. Atomic spectra was the experimental justification of the Bohr's model, you can say, in the reverse way. Okay, so this is the, and we discussed the different type of spectra. Let's say again, this is very important, that's why I am repeating again. What is the spectrum? As I mentioned, yes, let's say there is a discharge tube. Okay, in discharge tube there is any gas. As we are discussing hydrogen, so it's hydrogen gas, and now in hydrogen gas we are making electric discharge under very low pressure, and light is coming out. After analyzing that light that is coming out from here, we obtain some spectrum. What kind of spectrum that may be? Okay, so spectrum can be classified in various ways, just like it spectrum may be absorption spectrum or maybe emission spectrum. I will discuss this, but these are two kinds. Again, spectrum can be line spectrum, can be continuous spectrum, or band spectrum. These are all classification, but there are two different type of classifications are there. So first we have to understand this type of classification, the absorption spectrum and the emission spectrum. What does it mean? And then we will discuss this type of classification, line, continuous and the band. Okay, in last class we discussed this little bit, not little bit, discuss this, but again this is very important, that's why I want to make this very clear. So again I am discussing this part. So what is the absorption spectrum? Let's say this is the atomic discharge tube. You are giving some light, there is some light source here, light is going through this discharge tube and again coming out from there. Here is your detector. Okay, so what you will see, you are giving some light. This is okay, this is not the experimental setup used for the atomic spectrum. I'm just discussing the general way. Let's say you have taken some kind of gas in any tube, and you are giving some source of light, and the light is going through that discharge tube, through that gas, and there after that there is a detector to detect the frequencies of the light. So you obtain that. Let's say what we expect, because you are giving the all frequencies, this light source has all frequencies, so there must be all frequencies in the detector. Let's say if there is some, if you are dealing in the visible range, let's say some spectrum is missing, some line is missing, means it must have all frequencies, because it has all news it has. But let's say some specific news are missing. Okay, we are now in photographic plate. In this detector is basically a photographic plate. In photographic plate, now we are varying the frequency in the visible range. For our convention, we consider that it may be from 0 to infinity, nothing, no restriction is there. But to understand, because we can visualize only the visible range of the light of the electromagnetic spectrum, so we are now only consider that visible range. So in visible range, what should be the case? Here must be the blue part. Okay, after that here, and we can say not like that, let's say it should be VIBGYOR. Okay, so it must be like this, we should obtain this. Means if you say here must be violet, then must be indigo, then must be blue, so right, and after that green, not sharp distinguished, I'm just giving the idea. It should look like this. Then orange, where is the orange? Let's say this is the orange, and red. We should obtain this kind of spectrum. Okay, if you look, okay, but let's say in the photographic plate we obtain some missing parts, missing line. Let's say there is a missing line, like here is a missing line, here is a missing line. These lines are missing. If it is, these lines are missing, means the lines corresponding the frequency, this line, each line corresponds some frequency, so that frequency is actually absorbed by that gas while passing through that gas in the discharge tube. Light has all the frequencies, as we know, but the frequencies, some frequencies are absorbed by this light, by this gas from the light, so that can make that can use the energy of that photon to make some excitation or any other thing that will come into later, but that frequencies are absorbed. That's why their lines are missing in the spectrum. So that is called the absorption spectra, because the missing part suggested the absorption due to that gas. So this is the absorption spectra. So here I want to see, this is the absorption spectra. Here you can see this is original spectrum. This is just violet, then it is indigo, then blue, then green, then it's actually yellow, then orange, then red. So this is our spectrum, and you can see there are some lines. So these frequencies are missing in this atomic spectra, means these frequencies are absorbed by that gas. So same analysis can be done by using emission spectra. What is the just reverse thing? Here you will not give any kind of light. Here we are not giving any kind of light, so this is the absorption spectra. Okay, now you are not giving any kind of light, you are giving some energy, other source of energy. In previous case, the light was the source of energy. That's why the gas was taking the frequencies, the relevant frequencies from the light to make excitation. So now you are giving the electric current, electric discharge in the gas, in the discharge tube. So what happens, that makes the excitation, and after excitation the molecules will be again stabilized, and they will release the photons, the corresponding wavelength of the photons. So what we will obtain, and there is a detector, so light will coming out. So this was the experimental setup, right? As I mentioned before, the discharge is going on, no light is given here. The discharge, we have made some electric discharge, and that make excitation, and after excitation the light will coming out. So that is our emission spectra basically. So that emission spectra, what should that look like? Because this is emission spectra, so that must be black, because there is no light source given, but some frequencies are there because some excitation was occurred, right? So and after that excitation in the molecule, in the atoms, that atoms will be stabilized, and that amount of energy will be released in forms of light having some particular frequency or the wavelength. So that's why the similar kind of lines will be obtained. Here the indigo line will obtain. This is the indigo line. In blue region there is a line. After that, in yellow region there is a line. In orange region there is a line, and then in red region there will be another line. So this exactly the reverse thing, and it should be, because let's say here there are 5 energy gaps in this atom. There are 5 energy gaps. That means 5 transitions are possible. Okay, one transition requires the energy which correspond to the indigo range, one in blue range, one in green range, one in yellow range, and one in not in green range, one in orange, and one in red. So these were the 5 possible transition in that gas. So when you are giving one light, so that light have all the frequencies. We are dealing in the visible region, it has all the frequencies for indigo, blue, orange, yellow, red. So then the atoms will be excited, absorbing the photon from the light, and that's why these photons are missing from this spectrum that detected by the photographic plate. So that's why there are some black spots. Okay, this is the absorption spectra. Now the same thing happened. Now you are not giving light, you have excited by giving electric discharge, so that excitation already occurs. Now that atom will be de-excited, and while excitation, the required amount of energy is the same. When it will de-excited, the same energy will be released in forms of photon. So that's why the same lines, the position of the lines will be same, but now you will have the light, for that particular frequencies, okay, which correspond those energy gaps, those 5 energy gaps. That's why you will obtain the emission spectra. That is the emission spectra. So it is the just reverse things. Okay, so this is absorption spectra, this is emission spectra. I think it's now a bit clear. So here the same thing, it is totally black, and there is some particular line here where the lines were obtained in the absorption spectra. At the same places the lines are obtained in the emission spectra, but in emission spectra everything is dark. You are having just the line corresponding those frequencies for the transition happening in that de-excitation in that gas, and the same lines were obtained in the atomic spectra, but that lines were missing from the atomic spectrum because those lines was absorbed by that gas from the light. So that is the case. That is the emission spectra, and that is the absorption spectra. So don't be confused by that, but the essence, the physics is same. That's why the results are also same. But for the both absorption spectra and the emission spectra, there are some kind of classification, that may be line spectra, maybe continuous, maybe band. Here I have shown the line spectrum because the lines are missing, or we are having some lines. If you have the complete band, there are no line, then that is the continuous spectrum, as I discussed in the last, as I explained in the last class. So that is continuous spectra. But if you are having some bands, let's say for emission spectrum, let's say this is line spectrum I have already shown. So let's say for emission spectrum, what will be the continuous spectrum look like? Band spectrum. Continuous spectrum is clear. Continuous spectrum, that will have all frequencies, all wavelengths. But for the band spectrum, there will be some patches, like here is a band. That means there are so much lines that are closest to each other, so that will make some band. So this is a band spectrum. Let's say there is some band. So these are the band spectrum. Again, there may be other bands as well in between. So these are the band spectrum. Okay, so these are the classification of this spectrum as we discussed. I want to make clear this part. And the next, okay, so now we'll discuss the series. We have already discussed, but I will just summarize the series, and then we will move into the ionization energy and the ionization potential part. So I think in this part, let me stop here. In the next part, I will start from the series of the Balmer series, we can rather say Balmer series of hydrogen spectrum. Then we will discuss Paschen, bracket, hump and everything, and then we'll explain those results by Bohr's atomic model, and that is the beauty of the Bohr's atomic model, and then we'll discuss the drawbacks. So let me stop here. We'll again catch from here in the next part. Thank you.